I'll switch the language now because I would like to introduce our first keynote speaker. I'm more than happy to bring on our stage Peter Lawrey, who is low latency Java specialist at higher frequency trading. Those who attended the previous sessions of IT Days know Peter very well because he had at least one presentation in each of IT Days events. Peter has a popular blog called Vanilla Java, which has more than 4 million views, and he is very active on stackoverflow.com under Java and concurrency sections. Today he will talk about designing high-performance blockchain platforms on Java. Peter, please.
Good morning. Yes, this is, I think, my sixth visit to Cluj over the last 5 years, and I enjoy coming back every time. It's a real good vibe and a very positive, constructive feedback I find from the talk. So I really enjoy presenting in Cluj. Today I'm talking about design considerations in building a blockchain. So what we did was we designed our own blockchain, but from a high performance point of view, and I'm not talking so much about the platform, but some of the things that we considered in building that platform. So I'm a Java developer, Java champion. I have the most answers in the world for Java and the JVM on Stack Overflow. And I have gold badges for memory, file I/O, and concurrency, and that's in any language. I'm the only one to hold, or the first one to hold those badges. So it gives you some idea of my interest in bent. For the last 5 years, I've been the CEO of my own company, and so we have a small consultancy based around the UK. So a lot of tier 1 banks use our software for building trading systems, mostly libraries, which they then use to build the rest of the application. In some cases we help them do that, and particularly when they need to get to market quicker. So the main areas that we've worked on are smart order routers, market data distributors, and global position management. And so as an example here, this has got FIX, which is a particular protocol that's often used in financial institutions. It goes through a series of microservices and then goes out to the venue. The worst 1 in 1,000 was 19.3 microseconds. So that's a million, 19 millionths of a second to get from one end to the other through 3 microservices. And that's assisting 5 messages as it goes all the way through. So there's a lot of performance considerations in actually achieving that, and that's all in pure Java, by the way. So perhaps not an obvious choice, but it can be done in Java. So we also are very active in developing open source software. And we have a number of key libraries have over 1,000 stars. So they're quite popular libraries. I'll be talking about these in a little bit more detail in this afternoon's talk, but today I'm more looking at blockchain solutions. So one of the problems that I have with a lot of the blockchain solutions that are out there is that blockchain's been used as an exciting new technology, not necessarily what I consider to be a compelling use, as in, is this the only solution? Is the only way of solving this problem? So very often blockchain is used when in fact a database would have been just fine, and in fact may have even been a better solution than using a blockchain. Because blockchains don't have query capability, so you end up having a database sitting behind your blockchain so you can query it anyway. So what does the blockchain really add? And in particular, where we see a compelling use case is when you have multiple participants sharing a cluster of nodes and they don't have to trust each other, where that's an advantage to not have to trust all the nodes in the environment. So sometimes people use the term something like a private blockchain, but really what they mean is that all the nodes in the grid are trusted, they're all run by one provider, in which case you could have used a distributed ledger. And in many cases they are adapted, they were distributed ledgers and then were adapted to make them more blockchain centric. From our perspective, something unique is what's called, what we considered a public blockchain, which is a blockchain where the nodes themselves don't need to be trusted. They don't need to trust each other. They just need to trust the protocol, the messages they exchange with each other. They don't need to trust the operation of any of the individual nodes. One of our key interests is performance, as you probably already gathered, and so we compare a sort of a benchmark system. From my point of view, is Visa. Visa has one of the highest payment rates in the world, and they can sustain 24,000 transactions a second, although in reality, over a day, they get about 1,700. So the peaks are around 24,000, but their sustained is about 1,700. Now this is an established player, so if you're going to be high performance, you really need to be faster than Visa. Otherwise, you may as well use Visa because it already runs and works. So this is where our blockchain tends to run into a little bit of difficulty, and that is that the sort of transaction rates you can get with, say, Ethereum, Bitcoin are much lower. Bitcoin's about 2.5, 3 transactions a second. Ethereum can sustain, the global chain can sustain about 7. There are other technologies out there which get higher rates in the order of 500 to 1,500 transactions a second. I've seen a benchmark for Corda getting to around 6,000 a second, although it wasn't clear whether they used single chain or multi-chain. In any case, they're sitting behind Visa in terms of throughput. So, as you can see, they're a very small percentage of what Visa actually achieves. There is another problem, is that in being very slow, it also consumes a lot of power. And in particular, Bitcoin, if it were a country, it would be the 39th largest electrical energy consumer in the world. It's about the same as Austria. The significance there is that every individual transaction uses about as much power as a US household does in 10 days for every transaction. As you can see, that's not a very scalable solution. Ethereum, by comparison, is about 2.5 days of power, but it's still a lot. So what we did is we took the experience we had and came up with a design for a high-performance chain. And I'll come back to this slide, but broadly speaking, it's pipelined to process the data as quickly as possible with a very high throughput. And one of the key ways that it does that is that every node in the cluster can contribute a block to each round as concurrently. So every node can add a block to every round. So as you add more nodes, you can actually increase the throughput until you reach a saturation point. So if you have just a fairly modest server, the sort of sustained rates you can get are around 50,000, and it can peak at around close to 500,000 transactions per second. However, if you make the nodes larger by using a collection of boxes or just a bigger box, you can get sustained rates of around 400,000 transactions per second. And that's within a single chain. So a fairly obvious way to fairly obvious way to enhance that is to have multiple chains and support them running concurrently as well. So what we do is we focused on what are the key operations in terms of, well, what are we going to optimize? So one of the things that Ethereum and Bitcoin don't do, well, particularly Ethereum, doesn't focus on a particular kind of transaction. So we're going to do that really well, and transactions that are relatively rare, we won't necessarily do so well. So we're not going to bias one kind of operation compared to another. The reality is that most of the transactions are a very small subset of possible operations. And by not optimizing for those specific operations, they're going to be a lot slower than they could have been. So we've focused on 3 particular kinds of transactions, and in fact the first 2 are the key ones, which is transfer of value and exchange of value. They're the 2 key operations of any payment or exchange gateway, and if you can achieve that and make them very efficient, the rarer transactions are less important. So how do we do that? We focus very much on having a C-like Java framework, and with the C-like Java framework we have the advantage of getting very high performance out of our systems without necessarily making it harder to code in. So you can code in a more natural Java-like environment without having to get down to the very low level. Now in reality, most of the CPU power in a blockchain solution is spent doing signing and verifying. So the signing and verifying is computationally expensive and necessarily so to offer its protection. So that's actually all implemented in assembly using a library that already exists. So there's another key decision is not to design your own cryptographic mechanism. There are very few people that could do that in a way that's bulletproof, and then it takes many years for people to become comfortable that your solution is sound and not easily cracked. So it's very much the case that you really want to reuse an existing cryptographic scheme that's well understood and people are comfortable with. So in fact, in this solution, in a 64 CPU environment, about 40% is spent in assembly just doing the signing and verifying. And in fact, only 4 CPUs roughly spent in Java. So Java is a small piece of the puzzle, but it's an important part for its business logic. Achieving consensus, it goes through 3 phases. First, all the nodes gossip about what data they have, what blocks they have, because they're all replicating to each other these new blocks. Then they vote on which blocks should be included in the next round. And then when any node sees a majority of nodes voting the same way, then it can declare that all of those blocks are now included in the next round. The other thing is the rounds are very short, between 5 and 500 milliseconds, depending on how widely distributed your nodes are. And so that gives you many opportunities to achieve consensus. So let's skip that. Okay, so again, the key point of blockchain versus a distributed ledger is, do you have to trust all the nodes in the environment? Do they need to be run by one organization? Are they all run sitting behind a firewall necessarily? Doesn't mean that you can't take what could be a public blockchain and run it behind a firewall. What you may do is you might have a consortium of companies that will want to work together but not without having to trust each other. Those nodes share data as if it was a public blockchain, but then you don't give access to the outside world. This access is still restricted to the companies involved or the individuals involved. It's not necessarily just free for all in terms of access. And that's about protecting yourself from more mundane attacks like denial of service or just preventing direct access to the whole world. You just do it to a small subset. So one of the key aspects is that you want to prevent fraudulent messages being added to the system. So if you've got a distributed database, any one of the nodes with root access or sysadmin can alter the database in any way and therefore compromise the entire system. So what you don't want is any one node to be able to put in fraudulent transactions. So one of the ways of preventing that is to have every message signed. And because the only messages that a node can sign are its own, it can only transfer money out of its own account. Can't transfer money out of an account it shouldn't own. So that means that you can then trust any message that's produced because only the private key holder that generated that message could have created it. So then the problem gets pushed back to, well, is the private key held securely? So you have to ensure that that's the case, but if the private key is held securely, then you know that only the account holder could have created that message. So as I mentioned, very much designed this to optimize for throughput. So by optimizing for throughput, I focus on what are the things that can be done concurrently and what are the things that need to be done serially. So anything that can be done concurrently is a parallel problem. You can push it across to more nodes or more CPUs. And fortunately, most of the CPU power in a blockchain solution is devoted to something that can be done highly concurrently. And that is the signing and verifying. So each individual message can be signed or verified independently, so that you've got a very concurrent problem there. Also, all of the client connections, managing those is like in a web service, they can also be done concurrently. The key things that need to be done serially are the consensus model. So there's not a lot you can do to speed that up, and you're limited by the latency of your network. But you can determine how often this consensus you try to achieve consensus. It's a tunable parameter, so you can increase the threshold for how often you try to achieve consensus based on what you believe you can achieve for your cluster. The other key thing is how fast you can go through the transactions to determine what is the outcome of those transactions. And in fact, in the previous multi-node, bigger node configuration, the bottleneck is how fast it can just go through those transactions. At the moment, it can do only about 500,000 a second, and that's the throttle on the entire cluster. Another key thing is that you want to have regular checkpoints. So this is a fairly common thing in the high throughput solutions, is that you have checkpoints, say, on a weekly basis. The reason for that is that when you are exceedingly high transaction rate, it's not practical to just replay them from the start of time because you're running it close to the maximum speed that the system can run at anyway. So there's not that ability to just catch up years worth of data. So you want to have regular checkpoints. There's also another advantage, is that if you want to be GDPR compliant, you need to be able to forget certain transactions for individuals after a certain time period. And if you have to replay from the start, there's no way to forget certain data. So to achieve higher throughput, we support what we call peer-to-peer chains. So a fairly common model for improving throughput is to have a main chain like Bitcoin, and then have a side chain like Lightning, and a lot of the work's done on the side chain, and then that just regularly updates the main chain. So what we've done is we've deconstructed that further and just having everything as a peer chain. There isn't a main chain as such. They're all peers of each other, and that way you can scale. You're not bringing everything back to any one chain. So no one chain is a bottleneck. So we have a 64-bit ID for the chains themselves, so you can have effectively an unlimited number. We also have support for fix, because one of the key problems is how do you have a standard protocol for all of this, because whatever you come up with, it's not always clear that that's going to become the standard protocol. So instead we've fallen back to an older protocol called FIGS, which is a standard used in most banks in the world and most exchanges. It's not the prettiest protocol, but it is standard and it works. So I'm running low on time, so I'm going to skip through some of these slides quite quickly. So we support extending the platform. So this is, what we're talking about here is a library called Chronicle Decentered. The library itself is a framework, and in that you plug in your transactions. But the framework itself just requires you to implement two interfaces for your transactions. So the key bits are the gateway, which is right on my right, your left, and that gateway is the first handler of any request coming in the system, and it can bounce out any kind of query that doesn't actually need to go to the blockchain. If it does need to go to the blockchain, it passes it on, it goes through the consensus algorithm, and then the post-blockchain processor handles all the requests in the order that the blockchain is determined. So all the blockchain does is determine what transactions occurred in what order, but it doesn't determine their outcomes. And so the post-blockchain processor does that. So here's a simple example where all you're doing is passing text messages through the system. This is what a simple text message looks like, and all of the serialization and toString equals hash code is handled by the parent class. So then you've got a gateway that implements the method of the interface. That method determines whether it should be passed on to the blockchain or rejected, in this case. And lastly, once it's gone through all the blockchain, what do I do with the message? Well, that message has a destination address, and it gets sent to that destination if it's connected. And so this is what marshalling looks like. We use YAML a lot for all our toString for libraries and also for data-driven tests. But you don't need to use the framework at all. So the way we've constructed the framework is that you can take away the framework and test the business components completely standalone. So that's a key principle of the things that we do. Is you want to test your business logic as a separate concern to your infrastructure. So the infrastructure shouldn't be an issue in testing a business logic or how the business logic behaves. They're completely separated concerns, which means that you can test the business logic without the framework at all. So in this case, we just create the component, we feed in a message, we expect to get a certain message out. So in data-driven tests, you can put this in a text form. This is useful for constructing large and complex tests. And so this is the output. So the first message is rejected, and this, because the text is null, and the second message is accepted. So we expect to get this as the outcome. One of the benefits of using text out is that if the test fails, we do a text-by-text comparison in our IDEs, and it just comes up as, use the IDE for the comparison, and you can immediately see what's wrong. So we've got some tests that are megabyte in size, and if one number is wrong, then that could take a long time to track down. Whereas if you've got the IDE doing the text comparison for you, you can immediately zero in on what number or what string is out of place, and then you can see what the problem is. So we're up to question and answer.
Thank you. If there are any questions?
Hi, Peter. Nice talk, by the way. And did I get it right? Is the performance of the consensus algorithm, is the key of performance found in the fact that you minimize the round time. Would that be right? Would that summarize?
Yes, so that's one of the key aspects. So one of the ways we minimize the round time is not insisting that every transaction goes all the way around the world. So it's a fairly obvious optimization. So Bitcoin and Ethereum has to go all the way around the world, and then all the nodes in the world, broadly speaking, have to agree that a transaction occurred. Now, if I'm doing a transaction with you and we're both in Cluj, maybe it doesn't have to go all the way around the world. Maybe there can be a more localized chain for a more specific purpose that does that job. So by supporting many peer chains, you can have a peer chain that's localized to a particular region for a particular function. So it might be only FX transactions, and it might be based in London, for example. So that's one way of reducing the time. So then, at the moment, it goes through a series of phases. Every one of those phases the more phases you have, multiplied by the time it takes to synchronize between all the nodes, that determines your minimum round size. So there are techniques for reducing the number of phases even compared to what we have, but I've tried to go for something fairly conservative that I know will work. In future, we may be able to cut down the number of phases. Nevertheless, if you've got boxes that are reasonably well located to each other, we've been able to achieve 5 milliseconds round time. To some degree, the round time doesn't matter quite so much because every node can create a block. You can easily achieve the saturation point, which is the 400,000 transactions a second. So we've got a lot of leeway to adjust different things, such as the number of which nodes are involved in contributing to the chain, and how big the blocks are, and all of those things. So there's a lot of flexibility in there to achieve the throughput you might need. And the other thing to realize is that in a lot of the solutions we work on, people like to know that there's a lot of headroom, but they don't necessarily need it initially. And most likely, no one has a use for that kind of throughput yet, but they may find it reassuring that it is possible.
Thank you.
Thank you. Other questions?
Hi, Peter. Thank you for the presentation. First of all, my name is Andrei, and I don't have questions related to the blockchain itself, but to some technologies, or first of all, for the fact that did you have any other languages or frameworks besides Java that you considered before starting doing this, especially in the context of nowadays licensing changing in Oracle's politics? Mm-hmm. And the second one, I have seen that you are using YAML, and my question is what you're using it for, and why did you choose YAML? It's pretty popular nowadays, but it's for the user understanding, it's much easier to read, but other reasons, what are these?
Sure. Okay, so in terms of the licensing model for Java isn't so much changing, it's more the support model. So Oracle is doing releases every 6 months, and they're only supporting for free the latest version, which means that in most organizations where you can't necessarily just keep upgrading the newest version, you're more likely to get stuck either on a version that Oracle is no longer supporting, or you're going to have to pay for support, which is part of the logic for doing it. That they want people to obviously help pay for their support costs. However, there's quite a few alternatives. So there are both companies like Azul, which have a reasonably priced supported version of OpenJDK. This is not Zing, which is their high-performance library, high-performance JVM, but it's just a standard redistribution of the OpenJDK. So that's a commercially supported version. There's also Red Hat and Adopt JDK, which are free redistributions that are available for, so the Adopt JDK is available for Windows and Linux. So you could use those instead. Obviously not necessarily commercially supported, but definitely better than not upgrading at all. So certainly one of the things to be aware of is that Java 8 will no longer be commercially supported by Oracle after January. So in January, by March, the only version that's freely supported by Oracle will be Java 12, right? And I'm pretty sure no one here is even using Java 12 yet, it is available on early access, but you know, it's going to have a fairly aggressive cycle in terms of upgrades. On the flip side, because they are releasing much more often, so it was roughly every 2 to 3 years, now it's every 6 months, the changes are very minor. For example, the difference between Java 10 and Java 11 in terms of language is that you can now put annotations on parameters of lambdas, although they're ignored. So they're more like a comment. And that's it. That's pretty much the only language change between 10 and 11. In some ways they were seeing it more like, you know, like for example, when they went from Java 8 to update 20, then to update 40, then to update 60. That's the kind of cycle they're thinking of it, is that these are meant to be very minor changes between the versions. So, you know, I do see that more people will be willing to just keep updating them as needed, but there will also be people that will say, well, actually, maybe it's time to look at OpenJDK more seriously than we have in the past.
And related to this, have you heard about the D language, for example? Because compared to, well, of course, maybe it's not so easy, and there are not so many developers on it, but as far as I know, it has the possibility to create code which is with the garbage collector and without, and in terms of performance, this might be a very good thing, because you can control what memory actually you allocate and what not, you know?
Yes, I think having that kind of level of control can be useful. It's just not what most developers really are concerned about, in the sense that they usually got some sort of business problem that's been given to them, and for the most part they're asked to develop it and get it working as quickly as possible.
Yeah, that's the problems nowadays.
Yes.
That's why we get gigs of RAM and a lot of stuff that we usually not need.
That is another thing, is that hardware is continuously getting cheaper. When I started, I had a PC which had 128K of memory, and I programmed on it for about 6 years, and I never found a use for all of its memory, and all that time. Whereas today, you can, a lot of my clients have either 1/4 to 1/2 terabyte boxes, and they're, you know, again, I'm not sure that they're really using all that memory. It's just that, well, it'll be hard to upgrade it later, so let's just put in the memory now, sort of attitude. About your other question, YAML. So the reason we focused on YAML initially was that it's because YAML is designed to be human readable, which has some benefits and some disadvantages. The main benefit is that it can be more easily presented to less technical users or non-technical users, and it's not as off-putting as, say, JSON or XML, which are subsets of other languages. So XML is a subset of XGML. JSON is, of course, a subset of JavaScript. It wasn't necessarily designed to be human readable. The downside of YAML is that if you're using it for generic serialization, is what we're attempting to do, it's difficult to come up with, well, what would look nice to a human as part of your serialization logic, right? It gets quite complicated. And you can spend a lot of time worrying about whether there's an extra space somewhere, or whether you've used a comma versus a minus, none of which makes any difference to the computer, but it's all about human readability. It can make the library more complicated as a result if you're trying to output what is effectively pretty printed serialized objects.
Yeah, that's basically exactly what I wanted to say. That because of the problems with the human readable form, you will end up parsing too many stuff and converting many stuff that you usually don't need.
Yeah, it's not. A lot of the overhead from our point of view is just in supportability, because you end up with some very subtle changes that are kind of unimportant in terms of the serialization, deserialization, but can break certain tests, for example, just because the comma moved, or it decided that an array that could have been multi-line is now all on one line, because there's a lot of ways of rendering the same piece of information.
Okay, thank you very much.
Hello. So my question is related to the consensus mechanism.
Sure.
You mentioned this works on a vote-based consensus, and I was wondering, what does a majority vote means in the context where you also mentioned that the transaction doesn't have to go through the entire network or all over the world. How you establish the majority? What's a majority in that case? And
yes,
maybe even more details on the vote.
Sure. So one of the big problems of any distributed system is how do you determine who all the participants are? One of the benefits of Bitcoin is that it doesn't try to determine who all the participants are, yet it works anyway. So it solves the problem by avoiding it, which is a very smart thing to do. However, one of the downsides of not knowing the participants or having any kind of controls over it is that you can easily achieve a 51% attack. So there was a Bitcoin this year, a digital currency this year. They had 11,000 nodes, and yet someone decided to run up 12,000 nodes on AWS. Did a 51% attack, transferred some money out of the system. It was estimated that cost them probably about $250 of AWS time to achieve that. So we're looking to have a little bit more control over which nodes are participating. That's actually something that's pluggable. So each chain can determine how nodes can enter or will be accepted to the cluster. So again, it's a majority decision. So the majority of the nodes have to agree that in the next, so it's on a weekly basis. On a weekly basis, the majority of nodes decide who will be running the cluster in the next week, essentially. So you can't just enter at any time in the week. You have to enter the next week. So then you know all the nodes that could be running that cluster. So the worst case scenario is that more than half the nodes die and they don't come back. Then you're in trouble. That will cause some difficulty, but the benefit is that you can safely run a node with, say, nine nodes in the cluster. Nodes can't just turn up at random. They need to go through some process, and you can determine what that process is. They may be fixed, so it may be that there's no way for them to enter. It's like set 9 nodes, that's it. That's your entire arrangement. You can make it that it's sort of permissions-based. You could make it that it's proof of stake, and the stake might be a special token, which if it's 1, you can run as a privileged node. The values might be 1 and 0, for example. So you can use tokens as a means of distributing privileges that are transferable or delegatable to others, for example. So there are so many possibilities on how you might do it that we don't necessarily, we make it possible to implement all of those, but we don't say, well, this is the way you have to do clustering.
Got it, thank you. And the other question was, actually it's still related to consensus and voting. You mentioned that the nodes are gossiping and exchanging blocks and all of that. And my guess is that the next block is the one that's voted in the current round. So like there might be like a queue of 10 blocks or something that was generated by the network, and only one will move to the tip of the chain. Is that correct?
No, so what happens is they gossip about blocks, and then there's another node which is like a bit more like a tree structure, which says of all of the nodes that can contribute blocks, everything up to node block N, M, O, P are included in the next round. So every node can contribute a block which is included in the next round. And if one node is behind and it catches up, it could effectively contribute any number of nodes to bring it up to date. So basically they're all trying to replicate, they've all got a journal, they're all trying to replicate that journal, and when a majority agree that everything up to a certain block count for that node should be included, then it's included in that next round. So if you've got 9 nodes and they're all reasonably busy, you would typically get 9 blocks added.
Got it. So basically this centralized component will decide the structure or will link those blocks into the blockchain.
Except that it's not centralized. So it's all that voting is done in a decentralized manner. So they first gossip about what blocks every node is up to, and then based on that as gossip, they hear each other's gossip, they then vote and they say, well, everything up to this block from this node should be included, and everything up to this block for that node should be included. And if a majority agree that those blocks should be included, then at that point, any one of the participants can say, I heard a majority agree, and these are the messages that showed that a majority voted this way, and then it can publish that and say, right, at this point, for this round, all these blocks should be included. And so any one of the nodes at that point can make that announcement, and then that's what gets included in the next round.
Got it, thanks. You also mentioned you picked a specific signing algorithm. Were there any particular reasons for choosing that one?
The main reason for picking it is that it's the fastest one I could find that has a reasonable signature size. So the signature is 64 bytes, and on the service we've got, it can do about 200,000 verifies a second. 500,000 signings, 200,000 verifies a second on a single machine. Because this problem can be distributed, then within a single node in a cluster you can have multiple machines working on it, or you can have a bigger box. But it was mainly the signing and verifying speed. There is faster algorithms for signing and verifying, but some of them have very large signatures. So the fastest one that I could see on any benchmark has a signature of 800 kilobytes, which is quite a chunky signature compared to 64 bytes. And if you want to have a lot of transactions, that seems like it's not as optimal, but it's quite a bit faster. So it's a trade-off there. So we want to have small signatures that are also quite fast and still have in the order of 128-bit security, which is the compromise. And it's also been written by somebody else and it's been around for approximately 10 years. And no one's found any obvious flaws in it, so that's another selection criteria.
Got it, thank you. One last question, then I'll pass the mic. From what I understood, the focuses of these chains is to transfer value, right? That's the main purpose.
Yeah, or exchange.
Or exchange value. Are you considering enhancing this with something like smart contracts or something like that?
Yes, so in fact you can write any kind of contract you wish, and you don't have to have a coin. So an obvious use case is those, but as you saw with the message, there's no currency involved, it's just broadcasting a message, just to show you a trivial example. So the transactions themselves can be essentially anything you can write in Java. One of the key differences is that in Bitcoin and Ethereum, you're limited to the amount of state that you can associate with an account. Whereas in this case, you're only limited by what you can code. So the amount of state can be quite complex. A single account can have balances in maybe 100 or thousands of tokens, or you can construct other kind of state. But it's up to you to do that, though. So that it's arbitrary state as well as arbitrary code.
Got it, thank you.
Thank you. We still have time for one or two more questions.
So it's one of the key limitations of Ethereum is you can have arbitrary code that's Turing complete, but you can't just make up state, because then limits your function. You can't keep track of certain things.
So I would like to ask a question. It's about this concept that you mentioned, the saturation point.
Yes.
How does this evolve compared to the amount of hardware that you throw in? What is the limits, and are there any theoretical ways of exceeding it?
Yeah, so the saturation point is often the portion which has to be done single-threaded. So we do make a lot of effort to pull off a lot of work as possible to minimize the amount that has to be done single-threaded, but that's the saturation point. So there, in that situation, what you actually want is the fastest CPU you can get, or the fastest CPU for that workload. Which actually means a smaller box, generally, with a very high speed CPU. But for things like the signing and verifying, you actually just want lots of CPU power. So you may end up with a mix of boxes. So you have one box that has a very small number of cores, but they're very fast. And then you have more boxes that are cheaper, but give you more CPU power. So that to some degree, it's not too big a deal, because without going to all of this effort, you can still get 50,000 transactions a second, which is more than most existing systems. So that may be more than enough. The other option is that you may want to actually use the multiple chains for different reasons. Like you may have different purposes for them. You may want to use them for different collections or in different regions. So to reduce the time to consensus, you need to have the boxes within a region rather than going globally. So then you may have chain in, say, New York, Europe, Asia. And so by the time you've done that, you've now got maybe 200,000 transactions a second without doing any of this. So I'm not sure at what point you would need to go to 400,000, but it is an option.
Thank you. One more question.
Hi, you've mentioned that one of the key advantage of your system is that you can have local consensus, and this increases speed a lot. How do you get after this a global consensus without undoing like local transactions? Can you elaborate a bit on that?
Sure. So it depends on what your requirement is. So for example, if you're doing transactions within a particular region, say within the UK or across Europe, and you've got a bank balance or an account balance within that region, you can transfer money around without needing, for the rest of the world, even needing to know this. Once you do need to do that, you may then transfer the money or value to another region. So say you fly to South America and you want to do transactions there, you can transfer money into that region and then do, in terms, further transactions locally. It's only when the regions have to talk to each other that you need to transfer money between the regions, or value between the regions. And the way that's achieved is that a majority, every cluster knows not only which nodes are running its cluster, but any other cluster as well. So that when a cluster sees that a majority of nodes in another cluster transferred value to it, then at that point does it allow that transaction to occur between the clusters. Another key consideration is, on the top of my tongue, so there is a protocol for transferring value between regions or between clusters, and that's one of the key protocol decisions. And it's not as efficient, it does require more work, but as long as that can be minimized, then the number of transactions you can achieve within a region is completely separate and concurrent to all the other regions. Some of those clusters may be effectively private, just run by, the minimum is one node, run by one individual. You can run up your own chain, don't actually have to have it distributed, and it just runs anyway, and that could then transfer money, value in or out. So the key consideration that I was about to mention is that a chain itself has its own balance for the whole chain. So a chain cannot transfer out of it anything more than its balance of any particular value. That means that if you do a 51% attack on any particular chain, you can't compromise it, you can't use it to compromise any others. So the most you can do is transfer all the value out of it. That's its limit. So you can't transfer out of it more money than it ever had, and therefore just create money out of nothing. So that's another key consideration. So there's a protocol for transferring value between the regions, and you need to support that to be able to do that function. But within a region, you can add your own transactions to do whatever you want. So that is customizable.
Thank you.
Okay, thank you so much. We'll have Peter back on stage for another 30 minutes presentation after lunch break. Thank you so much, Peter, for your talk.